Welcome to the finale of our grid stability series. For over a century, the electric grid has operated as a one-way street. Massive centralized power plants generate electricity and push it down the line to millions of passive consumers. But that system has a massive engineering flaw. Because electricity historically couldn't be stored at scale, utilities had to physically build out enough wires, substations, and generation capacity to handle the single highest moment of demand for the entire year, usually the hottest afternoon of the summer. This chart shows exactly what that looks like in practice. Because the grid is sized for that extreme peak, on average, the vast majority of our electrical infrastructure operates at only about 55% of its total capacity. We all pay for that massive unused buffer in our utility bills. Worse, the grid operators maintain fleets of dirty, expensive fossil fuel generators called peaker plants that sit completely idle for 90% of the year, just waiting to fire up for those rare emergency hours. Building a deliberately oversized reactive machine was a brute force solution that successfully kept the lights on for the last 100 years, but that structural rigidity makes it incapable of surviving the demands of the next century. Right now, those aging centralized power plants are retiring at the exact moment electricity demand is skyrocketing due to the electrification of vehicles and industry. This graph illustrates the growing crisis. While the fossil fuel supply line is dropping, the United States alone needs to add roughly 200 gigawatts of new peak demand capacity by 2030 to keep up. Replacing those old plants with clean energy like wind and solar is essential, but it introduces volatility. The wind doesn't always blow, and solar output peaks at midday rather than during the early evening demand surge. Add millions of rooftop solar panels and electric vehicles pumping power back into the system, and that one-way delivery system becomes a chaotic, unmanageable web. Pouring more 19th century concrete won't solve a complex 21st century data problem. To maintain stability, we have to redefine what a power plant actually is. The physical hardware needed to balance the modern grid is already sitting in our neighborhoods. We call these distributed energy resources, or DERs, the solar panels, home batteries, and smart thermostats in our homes. When you network those isolated devices together, you get a virtual power plant. It isn't a physical building. It is a cloud-based software network that links these residential assets into one unified resource. The software coordinates the fleet. During a surge, the system automatically instructs smart thermostats to lower their draw, or triggers home batteries to discharge stored solar energy. In South Australia, tens of thousands of networked home batteries already act as a single generator. During a heat wave, this network can instantly inject 50 megawatts of clean power into the grid. That capacity replaces the need to fire up a fossil fuel peaker plant using assets that are already built and connected. Virtual power plants represent the new brawn of the grid, transforming passive consumers into a massive decentralized generator that supports the entire system. But managing millions of fluctuating energy nodes is beyond human capability. A human operator cannot track and balance the discharge of thousands of home batteries fast enough to maintain grid frequency. That requires artificial intelligence. Machine learning models act as the grid's brain, making the split-second load-balancing decisions necessary to stabilize such a complex network. This software also extends to the physical maintenance of the grid itself. Machine learning allows utilities to move away from reactive repairs and toward proactive prevention. Look at this model of a power transformer. AI models continuously analyze streams of sensor data, like microscopic vibration patterns or temperature spikes. The algorithm identifies these anomalies and predicts equipment failure days before a catastrophic event occurs. By catching these invisible issues early, the system can automatically reroute power around a failing component. This prevents blackouts and eliminates the billions of dollars lost to unscheduled downtime each year. We are watching the electric grid evolve from a blind, reactive machine into a dynamic and self-healing network. Edison's 19th century model relied on the centralization of power in one direction. By pooling decentralized hardware and managing it with AI, we are physically reversing that century-old architecture to meet 21st century demand. The devices in our own homes now act as an automated, decentralized marketplace, providing the balancing services once reserved for massive industrial power plants. Thank you for watching this 5-part series on grid stability. If you want to keep exploring how complex engineering and science shape our world, hit subscribe and let us know in the comments what system you want us to dissect next.